So at this point, all I've done is I've disconnected the battery. What changes?
Voltage?
To what?
0. Is there still voltage?
There's still a charge on the plates.
Okay.
So why don't we just start there? I disconnect the battery, and it's a nice, perfect disconnect. And so charge is now fixed. So I've got 2.832 times 10 to the negative 8 coulombs. Or rewrite it the way I had it over there too. All right, so I have my charge. It stays the same. All right, so the charge on the plate's the same. What about the electric field from the plates?
I guess if the charge is the same, the electric field would also be the same.
From the plates?
Yeah.
I think.
So that's still 800 newtons per coulomb.
Does this have anything to do with our formula that voltage is equal to the electric field times distance?
Voltage, yes. Well, that equation right there, so was just emphasized, since we're playing around with different electric fields here. There's plates, there's dielectric, there's total. This is total right here.
Oh, that's negative, isn't it?
The negative sign is just indicating that the potential drops in the direction of the electric field. All right, so sigma stayed the same, epsilon subnaut's a constant. I hope it stayed the same. So plates is the same. What about here? Either of these changed when I disconnected the battery?
No.
Epsilon, no.
No. Okay.
Epsilon's dependent upon the dielectric.
Yeah, right. So nothing changes.
Nothing. No.
So this stays the same. That's still 200 newtons per coulomb. The distance between the plate is the same. So what about the voltage? Voltage is basically electric field times the distance, ignoring signs. Did my voltage change?
No.
No.
So if my charge stayed the same and my voltage stays the same, what does that tell you about the capacitance?
Stays the
It
same.
also stays the same.
Yeah. So just because you disconnect the battery doesn't mean you suddenly trash the whole thing. It's you basically have charge stored on the plates. So this is 2.832 times 10 to the negative 9 farads. And some students get thrown by that. They set up the situation, then I disconnect the battery, or then I disconnect the battery, and occasionally a student will go, "Oh, wait, something had to have changed." No, not really. Not in our nice ideal board example. So now, let's make the distance half what it was before. So it was 0.05 before, so it's now 0.025. So I've now taken it and I've jammed the plates together. Somehow magically without discharging any of the charge. The dielectric accommodated by half as much dielectric magically disappeared. In other words, we shoved it together, everything else is the same.
Okay.
So this was original. This is plus dielectric. Disconnect battery. And so now we are, D is cut in half. So, yes, Brooke?
I may not have heard this quite right, but since now the dielectric is cut in half, that affects the distance. Does that change kappa? Would that change it to 2?
No, because the material is still the same.
Okay. Gotcha.
Well, the
And-
capacitance would double, right? Because we were dividing by distance and now the distance is smaller. Oh, wait,
Because the
No, that's
area
right.
is
You're right.
smaller too.
yeah,
You're right.
the capacitance should double.
Alright, so capacitance is doubled here, so this would now be 5.664 times 10 to the negative 19 farads.
And so we can just, everything that changes is going to be doubled, is that?
Some might be cut in half.
So, or somebody, okay, yeah,
Yes.
true.
Voltage is gonna be cut in half, right? Because now you're multiplying it by less distance.
Is the electric field the same?
Oh, no, it's not, because the distance changes.
Alright, so what, battery's disconnected when we made this change, so what is gonna definitely be the same no matter what?
The charge?
Yes. So once you disconnect the battery, there's nowhere for the charge to go. Again, it's a nice ideal board example, there's no humidity, no one's touching it or bringing anything near it where the charges can escape. Charges are stuck on the plate, so my charge stays the same, 2.83 times 10 to the negative 8 coulombs. All right, so my charge is the same. If the charge is the same, what else has to be the same? And this is still 4 square meters, and kappa is still 4.
Is any, nothing else is the same, right? Or is there something else?
There's at least one other thing that's the same.
Voltage again?
No, voltage will change.
Because we're changing sigma though.
Yes, we
Yeah.
are.
So I thought that would make the plates and the total.
Oh, wait, no, sorry, strike that. No, sigma stays the same.
Really?
Because the
But
charge
that-
is fixed and the area is the
You're
same.
right, you're right.
Wait, sorry, can you say that again?
Sigma is the same, the surface charge density is the same, because we haven't affected the charge. We still have the same charge on it, the area hasn't changed.
Oh, the area hasn't changed, okay. I
So
thought
sigma
you-
is still the same, therefore, what else has to be the same?
So therefore, the plates and, or the electric field on the plates and the total are also the same. Okay.
It's the same.
So that would stay the same.
Yeah. Or,
But the total doesn't?
Correct. Wait. No, actually, the total would stay the same.
yeah, it's the same.
Why does the electric field on the plates stay the same?
Because electric field from the plates only depends upon the charging area. Because the formula for electric field from just the plates is sigma over epsilon sub naught. Sigma is the surface charge density, so that's Q over A epsilon sub naught. Q is the same, A is the same, epsilon sub naught is the constant. Nothing changed.
Okay, that makes sense.
But voltage will change because of the distance. So I think it's back to what you had said before. Because E total stays the same, but delta X is now different. So what's our new voltage?
Five?
It's cut in half. We're storing just as much charge as we did before with half the voltage. We doubled the capacitance. Questions here? Let's connect the battery again. Reconnect battery. Now what? Same battery, reconnect same battery.
voltage gonna go back to 10?
It will. So I now have these plates that are closer together. We have a higher capacitance, and I've just doubled the voltage. What do you think that's going to do to the charge on the plates?
Is it gonna overload the plates or just increase?
In our nice ideal example, there's no such thing as overload.
Okay.
When you say overload, that to me, you get so much charge on there that it'll spark across
Right.
and burns a hole through the dielectric.
Okay.
And there's some interesting videos out there where people actually are testing dielectrics to figure out what point you'll burn a hole through it. And that's, if you hear a reference to dielectric strength, that's a reference to basically number of volts per meter, which is taking into account the voltage as well as the distance in order to burn a hole through it. And the one that I saw that I thought was excellent was not just some kid in his garage playing around, seeing how close he can get to killing himself. This was in a lab situation with someone who knew what he was doing. So anyway, so I doubled so I have a capacitor here, I just cranked up the voltage. What do you think that's gonna do to the charge?
It is going to cut the charge in half
Why?
because we just increased because oh no. I was thinking about the C, the big C, it's not coulombs, the
Capacitance?
capacitance. I was thinking of the capacitance because I thought that I'm
Wouldn't the capacitance stay at 5.664? No, wait, because the voltage is different
double the
now.
It's a
voltage.
parallel plate capacitor, I got this formula right here. Any of this change when I hook the battery back up?
No.
No.
So capacitance does stay the same.
And then the charge would double, right? From
Yes.
2.83?
Capacitance tells us the amount of charge we can store per unit voltage. If I double the voltage, I'm doubling the charge I can store on it. Another way of looking at it is voltage is this impetus to get charges to move. If I double the voltage, I am doubling my effort to move charges, so I will get, since I doubled it, I get twice as many charges pushed. So the charge will double when I reconnect it to 5.66 times 10 to the negative 8 coulombs.
I mean, the electric fields have not changed through any of this, so I feel like it's logical to assume that they will also not change.
Well, the electric field, well, the total hasn't changed at all, but from the plates it definitely has changed. So you're saying that the total will still be 200?
No.
What are you saying?
This thing, I don't know. I'm picking stuff up.
Isn't this the one situation where the total does change?
Yes, it will change from here.
Yeah.
Oh, therefore it would change from all of them. Going back to I have two total electric field total formulas. I got this one and I have this one.
Yeah. That's
So, well, D cut in half. My voltage is twice over. I guess D was cut in half earlier. From the previous step to this step, my voltage got doubled.
So it's 400 newtons per coulomb.
And now from the plates. get?
Hang on. Let me redo it because this does not look right. So I have semi charge. Okay, I got the same thing. 1,598.9.
I think you got a rounding issue there, but yeah, 1,600.
1,600, okay.
Because I had these two plates with a certain amount of charge in it. When I added the battery, I doubled the voltage, which doubled the charge on there. If I doubled the charge, I doubled the electric field coming from the plates.
Oh,
The
so,
electric
okay.
field from the plates depends upon the surface charge density, which is doubled.
Okay.
I have no idea how we're approaching this. So what I did is sorry, you can
No,
explain
no.
what you did, but at least tell me what I'm doing wrong.
Okay?
So I think I'm still hung up on this whole, what's that called? The 8.85 not being 8.85 anymore, epsilon.
Okay.
So I took the electric field total, and I solved for sigma by doing our new charge, 5.66 times 10 to the negative eighth, and divided it by the area, which is still 4.
Right.
So I took that number and I divided it by 8.85 times 10 to the negative 12 times 4 just for the epsilon part. Because that
Right.
should be epsilon with our new kappa.
Right. 4 times what it used to be.
Yeah. That should get the right answer, shouldn't it?
That should.
Okay, maybe it's just a calculator issue then, because I've got about 400.
That right there.
Oh,
You're solving for total.
never mind. Hold on. If I put in 8.85, I should get the right answer. Okay. I see.
Because since epsilon is kappa, epsilon sub naught, I'm going to do it on camera. So E total is sigma over epsilon, which is sigma over kappa epsilon sub naught, which is 1 over kappa times epsilon sub naught, which is 1 over kappa times the electric field from the plates. So if kappa is 4, I know that the total has to be a quarter of the total. This is a quarter of that.
What I did Anna was just divide 10 by 0.025 to get 400.
And then you could also find total from the ed equation. Delta V equals ed. Ignoring sign. I think your book uses ED. So therefore the electric field, the total electric field is the voltage divided by D.
Yeah. Does that make sense? That's like what made
No.
the, so like, could you just step to the side, Dr. Fox, for a second, so I'm sure. The delta V equals E total times the distance.
Yeah.
That's like, cause I was having a hard time too differentiating between the plates and the total and when they move. And so I just did, so the
Oh,
voltage,
divided by.
yeah, I just did
Okay.
10 divided by
Yep.
0.025 and
Yeah.
got the total. And I just think that's
Right,
the
right,
easiest way to do it.
I see.
And then the plates, you do use the 8.85. Yeah.
I see, okay.
Does that make sense?
Yes. Thank you.
Yeah.
Also notice, we started out with the electric field total and the electric field from the plates being the same, because there's no dielectric. So the electric field from the dielectric, E die, the magnitude would have been 0. We introduced the dielectric, so the dielectric now, we have a material in there that's getting polarized. I guess, assume that this is the positive direction there, so E die is now negative 600. Maybe it's a little long. So it's, the dielectric material polarizes to the point where we got the 600 newtons per coulomb of back electric field. Still says negative 600. We now shove them closer together. We increase the charge, we increase the effect, we increase the electric field here of 1600, which is going to polarize more of the dielectric, and so my dielectric is now negative 1200 newtons per coulomb. So we basically doubled the effect that the dielectric has. Alright, so this is the basic type problem. There will be a problem like this where you get a capacitor and then you start manipulating it, you get something different. Or not. The last couple of years I changed it around because I got tired of the same old problem, and so I did how can you manipulate the capacitor so that you double the voltage and keep the charge the same? With a list of, hey, here's the things you can manipulate. The dielectric, the area, the distance, I guess physically, anything else I can manipulate? The voltage of the battery. So let's just go through one of those. And then a couple of years ago I did one, how do you manipulate this so that this other thing happens? And it turned out to be an impossible situation.
Sure, they loved that.
Yeah, so on the next year I threw in the extra clause of, if it's impossible, show that it's impossible.
That's funny.
And I'm about to erase this stuff. Any questions before I erase? I'm going to leave the equations up off screen.
I will say, for clarity's sake in teaching, I really appreciate that you've put like variables on the board and we're working through them kind of in the systematic way. Like something about that really